Microscopes and various forms of interferometers have been used for decades in optical metrology of objects that are typically larger than the wavelength of light, lambda. Metrology of sub-wavelength objects, however, was deemed impossible due to diffraction limit. In this work, we report the measurement of physical size of sub-wavelength objects with deeply sub-wavelength accuracy by analyzing the diffraction pattern of coherent light scattered by the objects with deep learning-enabled analysis. We are testing our technique using the simplest of objects, 1D slits, which are fully described by their width. We have randomized the width of 840 slits in a range between lambda over 10 and lambda over 2. Slits were focused ion beam milled in a thin chromium film and measured using a scanning electron microscope after fabrication. Then, we imaged the sample in a conventional microscope. A coherent light source at 633 nanometers was slightly focused on the sample, and the transmitted scattering pattern was collected by a high numerical aperture lens into a CMOS camera. Scattering images were collected at 4 different imaging planes, when the sample is focused, and at a height of 2 lambda, 5 lambda, and 10 lambda. This process was repeated for the 840 slits in a semi-automatic way. The diffraction patterns collected from the slits were processed in 2 different ways. The first one, by extracting the total intensity captured on the camera. The second one, by collecting the 1D diffraction pattern. Therefore, we can perform 2 types of experiments. We can train artificial neural network with 756 known slits, that is, the total intensity or the diffracted pattern have been fed to a neural network together with the real width of the slit. We measure the width of the 84 remaining slits with the trained neural networks. We have performed 100 realizations for each type of measurement and for each height. We found that an artificial neural network trained with only the total intensity is capable of retrieving the width of an unknown slit with an accuracy of lambda over 20, surpassing the diffraction limit by an order of magnitude. Even better, when feeding the whole diffraction pattern, this accuracy increases to lambda over 260, or 2 orders of magnitude better than the diffraction limit. This result brings artificial intelligence-enabled optical metrology to the nanoscale.